All right, so let's go ahead and do the other second little video for nuclear physics, and this time we're getting specifically, at least starting with nuclear, and I don't know why I write so poorly with this thing, radiation. All right, nuclear radiation. So it turns out that, as we talked about before, electrons, their orbitals and their states, they have specific quantizations that occur. So only certain energies can be emitted from the electron orbitals and absorbed from them, and it has to match those certain orbital levels that the electrons can obtain, and this was due to the interference pattern of them acting like waves around the nucleus, right? Well, it turns out that the nucleons in the nucleus are actually quantized in states like that too. They have specific states that they can be in, and therefore energies produced from nuclear decay is quantized with specific values, uh, just like the electron orbitals were, but these correspond to the energy levels of the nucleons. So let's look at an example of alpha decay. And what we can have is the example, what is this, radon, right, 226, and we can have it decay, so this will be actually alpha decay, okay? And what will happen is it has two different levels that it can decay down to. It can decay down to a higher level or a lower level. Okay? And so when it decays down to this lower level, what you get is an alpha particle that has high energy. So this is a high E alpha particle. And when it decays to this lower level, you have an alpha particle here that's got a low E, lower energy, I guess. Uh, and you end up, of course, it drops down to a lower element. And but basically you have this alpha particle emit, which is, if you remember what an alpha particle is, it's basically just a helium atom. So that's going to change what element we're looking at. And these ones that drop to this higher energy level that happen to go there, they'll go ahead and decay even further and actually produce, then you have this gamma decay as it decays down to the lowest energy, because things in nature want to get to that low energy. And what you would have here is then a gamma particle. So this would be gamma being produced, gamma radiation. And you have these kind of things. And you can go through and you can see that these different specific energy levels of alpha particles and lower energy alpha particles, along with the certain energy level of this gamma radiation, it gets produced. And you can build a little graph up of this kind of thing. I'm kind of going to make these numbers up here as I go through, because I don't know it for this specific example off the top of my head. But if you graph energy, different energy levels, according to their frequency that they occur, so frequency of occurrence, so how often these different energy levels occur, what you would find is something like this lower energy one might occur less than the higher energy one, so you might have a bar this high, and then you go up to the next energy level. So let's say these are other possible energy levels like this, and you'd get some different distribution of how likely different ones were and how often they occur. And this is usually a pretty useful tool statistically. So perhaps this decay occurs 3 times as much as this decay occurs, and so you can figure out what it is. But you typically get this kind of a distribution of different energies that are quantized. You're not getting little energies in between. You're getting these specific ones distributed. But you should definitely know how what this kind of graph is telling you. It's telling you that you're more likely to get an alpha particle of this energy than one of this one, or you're more likely to get a transition of this one by this one. And it should be, of course, to scale. So if this line is twice as tall as this one, then you're twice as likely to get that kind of an energy level. Okay. Outside of that, the next kind of nuclear radiation that we have is gamma. Well, uh, we just looked at a specific type of decay that produced gamma. Right, this was alpha that produced gamma. It was produced there even with alpha decay, which is what happens a lot because gamma does occur. And gamma radiation has a wide range. The important thing about this, a wide range of discrete energies. So it's quantized. Uh, it's quantized definitely, but there's a lot of different quantizations that can actually occur with this kind of radiation when gamma decay occurs. So we basically already talked about that when we talked about this, that it's usually accompanying other types of radiation. I think specifically even this alpha decay. The next one is beta decay. Okay, so beta decay. Well, it turns out if you do this same sort of graph, this frequency of beta decay kind of graph, right? So if we make that same, uh, you know, frequency of the beta decay, and then specifically look at how much energy the beta decay has, so how much kinetic energy is coming out of them, it turns out that uh, this actually doesn't look discrete. It takes a shape. Sorry, I'm trying to draw this nicely. It takes like a shape that trails off like that. Okay, and it's not quite discrete. It looks very continuous. But this continuousness of it, which really didn't fit the quantization that was being seen elsewhere, was explained with the idea of the anti-neutrino being produced with the beta decay. If you remember the beta decay had to have that little anti-neutrino in there to account for that momentum shift. Well, that missing little bit of momentum, well, if you look at that antineutrino, what happens is the energies that are produced when you add them together would be discrete, but individually between the two, the division of the energy could be different. And so you might have it occur where most of the, more of the kinetic energy goes into the antineutrino than at other times. So it gives you this kind of discrete not discrete, this continuous looking curve because the energy is split kind of randomly between the neutrino and the electron that is produced. All right? So it looks discrete, even though if you looked at the total, it wouldn't be discrete. Okay? So those are our three types of our radioactive decay coming from the nucleus. And now let's actually take a little closer look at the half-life, the radioactive decayness of this, right? So radioactive, we talked about this previously, but let's do a little bit more with it, specifically half-life, specifically more mathematical treatment of it here. So the rate at which the particles decay at, so rate is change in something over time, right? This is basically, if you're getting to the point you're in calculus, this is the rate of change of n, and that's going to be actually proportional to n, which should make sense because in radioactive decay, if we have twice as much of a substance, we should have twice as much radiation coming from it, because it was that whole probability thing where you had a 50-50 chance. If I flip twice, if I flip 100 coins, I'm likely to get 50 tails. But if I flip 200 coins, I'm likely to get 100 tails. If tail was radiation, so basically doubling would double up the rate at which I was losing them. So at 200, I'm having 100 decay. At 100, I'm only having 50 decay, and you can see that. So what we can do is write a little equation for this, and that's dn dt. This is sometimes dn dt could also be called the activity of it. So call this, we'll just write it over here. This is sometimes called the activity, and it's done with an A. And so in a lot of these results that I'll show here, you can just swap out in for your total number of particles in for activity, and we're going to set this equal to some negative, some value there, some constant times n. And we're going to call that constant, lambda, we're going to call it the decay constant. Decay constant. And it is essentially the probability per unit time of decay. So it's probability per unit time of a particle decaying. Okay? So this is what we get. And this is the differential equations. And there's, you could go through, you could separate the variables. I'm not sure if you've learned that in your math classes yet, but I could move dt over to this side, move n over to this side, and then do the integral on both sides, and I'd have, you know, an integral of 1 over n, that's going to give me a natural log, and all this kind of stuff, and you can go through and basically figure out what n is. Or you could go the differential equations route, which is to basically guess a solution, then check and see if that solution works. So we've done something kind of similar to this before, where we're taking the derivative of something and getting back that same thing changed by a constant. If you remember, we did this with simple harmonic motion. We got that. That was that Hooke's law. Was very similar to this. And so our solution to this is actually pretty simple. We have to have this negative constant, and it's that n, the amount of the substance remaining, is equal to n naught, which is the initial amount of your substance, times, well, what can you take the derivative of that gives you the negative of your original function times a constant, and that's this one, e to the negative lambda t. So if I take the time derivative of this, what am I going to get? I'm going to get negative lambda e to the negative lambda t. That would be essentially getting this back. So if I use this as n, take a time derivative of it, I'm just bringing that negative lambda out, right? Use the chain rule on it, and you get n naught negative lambda e to the negative lambda t. So that's basically my original n times negative lambda, because my original n was just n naught e to the negative lambda t. Take the derivative, all you're doing is basically go through and do it. You get a negative lambda out in front, and then n naught e to the negative lambda stays the same. So this solution does work. It does fit our differential equation right here, and it is therefore a solution to it. And since this activity is proportional to n, because this is proportional to n, right? That's our activity, then we can rewrite this. Like I said, you can always, pretty much always rewrite this as activity, current level of activity is equal to initial activity times e to the negative lambda t. Okay? And that's because activity is proportional to this. Like we can come over here and write activity equals that. And so that if it equals d and dt, and that's proportional, and it's also proportional. So this is another version of it that you can use. You don't necessarily have to be given the number of particles. You can just look at how much the activity is changed, because counting the total amount of particles can be rather difficult. And then take a look, if we graph this out, this is a decay, then we get the familiar decay curve that we did before. So time, and this would either be your amount of sample left, or or activity, and it would do that decrease that we talked about before, that as it goes down towards 0, and we would basically get this. So now, what if we wanted to use this to actually calculate out what the half-life is? And we can do that. We can basically say, well, before we did this, what did you do? You came over here, you looked at a spot on the graph, and then you went till it was half that amount left, right? And you said, okay, here half of this was my original amount, here's half of it. And then you came over and you brought the graph down and you said, what is this change in time that occurred here? That was the half-life, t sub 1/2. Well, we can also just say, well, let's look at n. How much do we want left? We want half the original left, and that is going to be equal to n naught e to the negative lambda t to the 1/2, t sub 1/2, the half-life time. So after the half-life is gone by, the amount we'll have left is half of the original amount, right? That's the original amount over 2. All right, so n naught cancels, and you basically have to go through and just solve for t sub 1/2, the time for half-life. So this is 1/2 equals e to the negative lambda t to the sub 1/2, so the half-life. And then this could just be 2 equals, take the reciprocal of both sides, lambda t half-life. And then how do you get rid of this? You take the natural log of both sides, and you'll have the natural log of 2 is equal to lambda, because remember, natural log is an inverse operation for exponentials like this, for Euler's number there, t half-life, and then just finish it off, t half-life is equal to the natural log of 2 over our decay constant, okay? And that right there, you don't really need to memorize it if you can remember how to just do this little bit of math, but it basically gives you the decay constant. And remember, you could go through and get this exact same result if you changed it to activity. So if you had started with activity, half the original activity is equal to e to the negative lambda t 1/2, where the activity cuts in half, activity cancels immediately, and you're right back to just this step. So you could continue on over in this step, and you'll get the same result doing it with activity or without. But basically, that's how you can look at the activity of something and calculate what its half-life is just by measuring that activity, the rate at which it is decaying, right? dn dt. So we can do one more thing with this. If we start with, I'm trying to see if I can keep this on here. So if we use n equals n naught e to the negative lambda t, right? If we use this and divide n naught over, so n over n naught equals e to the negative lambda t, and then take the natural log of both sides, so natural log of n over n naught is equal to negative lambda t, and then this is negative, when you remember when you're dividing natural logs, this can be expanded out as natural log of n minus natural log of n naught equals negative lambda t. And then, of course, natural log of n is equal to negative lambda t plus the natural log of n naught, okay? And this is essentially now in y equals mx plus b form. I gotta move this down a little bit. This would be y equals mt would be x plus b would be this, because natural log of the original amount of your substance is of course a constant. And again, you could have started with activity, so all of this, you could replace all the n's with a's, and you'll get something very similar. But then if we go to graph this, if you look at it, we have a negative slope and we have a y-intercept of the natural log of n naught, right? So if we graph natural log of n versus time, we should get a negative slope, right? Let's do that in a different color. You're going to have a negative slope. Oops, that was bad. Let me get rid of that. That was not very straight, but you're going to have a negative slope. Not that that was super straight either, but a little straighter. You're going to have a slope that's negative, right? And the slope of this will equal negative lambda for your decay constant, and then this interception here, where it intersects at time t equals 0, of course this would be the natural log of n naught, the amount that you had. So this is a way you could go ahead and graph this out, and so you could replace these n naughts with activities and get something very similar. Okay, that's all.